Hello everyone, welcome back. This is Lecture 6, Image Classification. Today we're going to introduce classification, supervised learning, key nearest neighbors, Bayesian classifier, support vector machines. To begin with, let's review the question we raised in Lecture 4, in which we are trying to group different images there. In the last lecture, namely lecture 5, we have introduced the clustering, which can group such images into different clusters. This can be done automatically. It's like the computer is drawing the circles by itself. That is also the reason that clustering is called unsupervised learning, because the human being doesn't have to tell the computer what to do. There's no knowledge inputted into the model, and there's no any supervision in between. It's completely data-driven. It sounds good, right? This can be done automatically, and we don't have to do anything. But what if we have some new examples? We call them unseen examples because we have never seen them in a data set. So how to find which group they should belong to? Do we have to rerun the clustering every time we have new examples? What if the feature representations are not consistent with our understanding? For example, in previous example, we actually are grouping based on if they're Asian, white, or Africans. What if the task is not for such kind of classification? It's rather to determine the age of that example. Can that representation be used, or can clustering can be used? Probably not. However, fortunately, we're able to tell a computer about our understanding actually. For example, we can give them labels. Let's go back to the examples we have previously, and because there are some images are available in our datasets, we can call them scene example because they are available there, and we can put some labels for them to represent our understanding about those examples. For example, we can use a W to represent the white. We can use the A to represent the Asian, and we can use the B to represent the Africans. So those are labels. Labels can tell a computer our understanding about those samples and those data as well. Then during the testing, we probably will have more samples which are unseen because we have never seen them before. So in the testing, the task now is to give the samples for those unseen images because they're not available when the training has been done. So we have to predict the labels of those samples. The prediction is based on our understanding given in the training examples there. So the task of doing this is called classification, is to predict the labels of those unseen examples based on the knowledge learned from the training examples there. So now you might have to pay more attention about those terms because we're going to use them frequently later in this course. So the first one is the learning, because we are learn something from the same example, and the process of learning called training or learning there. And also at the same time, the knowledge has been used. That's here are the labels actually representing our knowledge, our understanding about those samples. So at the same time, there are unseen examples and the testing phrases is the actual prediction part. The process is called um, machine learning because we're teaching the machine to learn the knowledge we have given. And also this is called supervised learning because there is supervision. We are giving the knowledge, we are monitoring the process of training. So it's called supervised learning. And after training, we will have a model. The result is a model. The model can be used for doing the prediction there. Don't be frustrated. There are just too many terms today, but I can draw something for you to help the understanding. First, let's see. We have some saying example there, and we have labels for them there. So we're giving labels, or something like that. Then these labels are representation of our knowledge or our understanding, and we will use that to teach the computer to learn, and we call them training. And also those same example are also called training example in between, and this is also called learning. The result of that learning is a model, and we will explain what the model is. And the model can be used for prediction, and so the prediction will be done on those unseen examples there. And the result of those prediction is some labels. And labels are called predictions as well. So the process of predicting labels are called testing, which will test how good the model is. So these are the relationship of those terms. Let's get started to introduce what the classification process is. Then you will be more familiar with them gradually. Before we introduce any specific algorithm there, I would like you to consider in this scenario where we have a set of saying examples here. That's the saying examples, and then we know what they are, and then we have to determine what this is. It's an unseen example. So naturally, the easiest way is actually we can compare them to each of the examples we have, those same example, I mean. So we can compare to this, and we can compare to this as well, and we can compare to this as well. And then we found that these two look like very similar to each other, and we probably will assign the labels of that example to this unseen example, and we know it's a laptop. So this is called instance-based learning because we are comparing between the instances to find the labels for unseen data. Well, to compare one image to the images you have in the data sets and to figure out what is the most similar one. Does that sound familiar? Yes. And if you recall the image retrieval we have introduced in the last lecture, and we can actually use the image retrieval to do something, to do the classification. This is the idea of kNN classifiers. The NN stands for nearest neighbors, and a K stands for the number of nearest neighbors. And at the very beginning, we can set a K to a specific number, for example, 1. That means we will search over the top 1 nearest neighbor of the unseen examples. If you're using retrieval currently, you can consider the unseen example as a query. So we will take the top K Here k equals to 1, we will take the top one from those ranked list, those images in the data sets out, and we will check out its label, and then we will assign its label to that query. That means we can use the label as a prediction of the query image or the unseen image currently under investigation. So there is a Chinese saying about that I think you're pretty familiar with. Let's let's see how it can be done in the feature space. So let's see, we have a lot of examples, same examples. We can project them into the feature space like this. And right now key equals to 1. Then here comes an unseen image, and we have to determine its label. And then after the retrieval, we know that this image is the top one in the rank list. That means the most similar pictures or image, well, with that unseen example. Then we will take the label of this example and assign it to this unseen example as a prediction for it. However, by setting the key to 1 will make the selection process a little bit arbitrary, because you know that feature vectors are usually with some noise and there are some variance there, and it's easy to be wrong when you just refer to one nearest neighbor. So most of the time we're setting k greater than 1. For example, we can use 3 or 5. In that case, we're not taking the labels directly. Rather, we're doing some kind of voting in between to take the dominating label among those nearest neighbor to assign to be used as a prediction for the unseen example. Let's see what happened in the feature space. Right now we have the k as 3. That means for each of the unseen image, we picked up the top 3 nearest neighbor from the ranked list. And then we can do a process like a voting by investigating the labels of those 3 nearest neighbor. You will see the label of A right now equals to 2. The number of W equals to 1. So the A is a dominating label here. In this case, we will assign the A, that means Asian, to this unseen example, and it will be more robust than just picking up the top one nearest neighbor. Okay, classified by retrieval sounds straightforward. However, that is just the easiest case for demonstration. In real applications, this is what we're gonna have. The samples from different classes are usually overlap to each other. When you're using the kNN, it's not easy because you're gonna be wrong. For example, if the unseen example is at this position and the nearest neighbor will be from the other class there, so your prediction is gonna be wrong, especially in this region as shown here. By observing the figure, you might think, is it possible to teach the computer to draw circles? Once we have the circle, we can evaluate each of those samples. I mean, how much it falls into different circles there. Then we could use the label, the class, the circle it belongs to as a prediction. So there is a method called Bayesian classifiers actually are doing very similar thing. Okay, before we introduce how we can draw the circles, let's assume the circle has already been drawn there. Then in this case, we have two classes there. One is A, the other is B, as shown here. And there are two circles for them. And there are some region overlapped by A and B. And we can consider each of them as a set. With that setting, we can determine the label of an unseen example x here in a more decent way by calculating the probability of A given the x. And also at the same time, we can calculate the probability of B given x. By comparing these two probabilities, we can determine the label of x is A or B. However, most of the time, the probability of A given X cannot be given directly. It's rather being calculated with the Bayesian theorem, like shown here. Recall what you have learned from statistics. You will remember this one. It's actually saying that the probability of A given X equals to this probability of x given A and multiplied by the probability of A and divided by the probability of x. So because these px are the same when you're calculating the probability of B given x, so we can ignore this part, just compare this part to this part. So this is what's happening in a Bayesian classifier most of the time. Let's see how we can estimate the probability. I mean, each of those probabilities we need, because A and B, as we have introduced, are two sets. So we can calculate the probability of A and B just by counting numbers. Say we can count how many examples in A, and we divide it by the total number of A and B, then we have probability of A. In a very similar way, we will have the probability of B. So we have these two already. Then these are actually called prior probability because they can be calculated in advance. So let's see, the other probability we need is the px given A, and that can be actually counted by using this one. The number of x divided by the A, that means x divided by this whole A part. Similarly, we will have the probability of x given B, the conditional probability. Sometimes we call it likelihood. Then we have these two as well. So with all the probability given, we can calculate approximately calculate the PA given x and PB given x. Then in that case, we can compare these two probability, and it's the PA given x is greater than PB given x. We will assign the label A, otherwise we'll give the x a label B. This is actually called naive Bayesian classifier. It's quite simple, so it's fast, and it can be extended to multiple class problem, and it requires least training examples there, and it works well for categorical data. The reason it works better for categorical data is because we have to count the number of x. So in categorical data, and it's discrete, so we can count the number easily. However, for the continuous data, if A is continuous, it's not easy to determine how many x are in the data sets. So we have to impose more assumption, but that's beyond the topic today. We're introducing naive Bayesian because we just want you to know they are one of the most representative example of traditional machine learning because it's created a model that's actually the distribution of two classes there. However, there are some disadvantages there as well because the features are supposed to be independent to each other. This is not true in many real-world applications. And there are some zero frequency problem that is for some of the samples, they they don't appear in the data sets. So when we're counting this number of x, they are gonna be 0. However, we can use another method to compensate this. The Bayesian classifier is actually estimating the distribution. So you see there we have A and B. Let's take one dimension, then it will be a bell shape like because a normal distribution. And this is the model of A when we have the samples, we're actually calculating how the shape will be like and where it distributed along the x. And for the same, we're calculating the model of B at the same time. So then the two do have models there. So when you're extending this to higher dimension, for example, if it's 2-dimension, the model will be something like a bell, like what we have seen. It's just like you rotate this as using the z axis, and it will give you the bell-like shape I have shown previously in the other when we're introducing the shift actually. So in 2D's case, the model and distribution and the shape will be something like this. So in that case, you will have two distribution bell-like, two bells there, and you can calculate the x there. The posterior probability there to determine which class this sample belongs to. So it's a decent method, and it's simple and it's fast. And so it was really popular previously. And it is popular right now in some of the applications. Another really popular and representative one is called support vector machines, and we're also going to introduce it today. Let's look at the feature space, and you will see to find out the classes is actually equals to divide or separate classes in the feature space. To separate samples of different classes in the feature space. In that case, we can actually draw a line like this. Those above that line will be one class, and those below that line will be the other. And because every line can be represented as this. This is what we have learned in high school in geometrics. So for any of the x, once we have its coordinates, we can actually calculate this part and compare them back to 0. If it's greater than 0, then it will above that line. Otherwise, it will below that line. So, in that case, you will see that we can construct a function based on the line, based on the formula of that line. And here it's saying x is a function like this. We can the output that function is either 1 or it's can be -1. So that means when it's equal to 1, it's above that line. When it's -1, it's below that line. So we can, in this case, we can actually do the classification based on the model of this dividing line, or sometimes we call it decision boundary. That's really straightforward method. And however, there might be a lot of lines can do the job to separate the samples from different classes there. However, which one is the best is the question to answer. after we have that assumption. In SVM, it uses a margin to determine how good the separating line is. Let's see, once we have a separating line, this one as an example, there are some samples are closest ones to that decision boundary or separating line. We call them support vectors. Then with that support vector, we can calculate how close they are to this separating line, like this one, and those are support vectors. And after that, the calculation, we know there is one margin, actually this one, which are indicating how close the support vectors are. I mean, the support vector from different classes are. The larger the margin is, the better the line is, or the decision boundary is. Let's draw another one with a bad example. So for here, you will see in those examples, some of the support vector lie on that separating line. The margin is supposed to be something approaching 0. So this is a bad example of separation. So in this way, we can evaluate how good and how well the separating line is or decision boundary is. As you can see here, the SVM is actually looking for geometric solution which is aligned to divide these two classes. And so it's a geometric classifier. And by contrast, as we have introduced the Bayesian classifier, it's actually called empirical classifier. Empirical classifier. That is, we have two bell-like shape representing this class, and those are also models for these two class. And actually, the risk of classification is determined by this part. If we put them into one-dimensional space, it will be something like the risk is determined by this area, and this is a model of A and B, and that's what we have learned in the statistics. I will not extend those more because this is just a course for beginners. We are going to introduce some of the concepts rather than the details, and indeed we will give more details later. To learn SVM conceptually, that's actually is all about SVM you need to know. But I know some students would like to know more about from inside. I mean, so in that case, we're gonna introduce more tricks used in SVM to help you understand what's happening in between. The first thing is, in previous example, the samples of different classes are actually well separated. And there's no any overlap. However, in real application, you do have those overlap in between, like those example. So the first trick used by SVM is to set a tolerance score, which can tolerate those kind of calculating to allow you can calculate the margin in between. This is the first trick. I'm not going to introduce more details, and just remember. The one we have introduced previously actually called linear SVM because we're using actually a line to separate classes. But in real application, you can't use a linear one to do it because those classes are possibly distributed something like this. Those are positive examples. Those are negative examples. It's not easy for you to draw a line to separate them because the decision boundary is supposed to be a nonlinear one. And in that case, we have to build a nonlinear decision boundary or separating line there. However, there's another trick used by SVM will help us to use a linear separation line to separate the nonlinear, the overlapped data sets. And this is another trick I'm going to introduce. To illustrate that, I will go back to one-dimensional space for easier understanding. So let's see, there are two groups of samples in the linear space. They are also point along that line. And this is a case that linearly separatable because we can use a line. We can draw one line to separate these two classes. However, the second example here is not the case because you could see here, it's not easy to draw a line. Whether you said here, you miss here. If you said here, you might miss there. So it's not easy for you to draw a line, or in one-dimensional space, is just find one single point, separating point, to divide that two classes. So it is too hard in one dimension. However, if it's possible, we can actually map this one-dimensional data into higher dimensional space, for example, two-dimensional space, like this. And you will see that right now in this two-dimensional space, it's much easier for you to draw a line to separate these two classes. So this is actually a trick used by SVM by mapping the lower dimensional data into higher dimensional space, because in the higher dimensional space it becomes sparser. I mean, the distribution of classes becomes sparser, so it will be much easier for you to draw a line, or in higher dimensional space we call them a hyperplane as a decision boundary, something like this. So here's the idea, and actually to map a lower dimensional data to a higher dimensional space, usually we're using a mapping function like shown here. So by applying that mapping function, we can map each of the sample into the new space there. In that case, we can draw a line or a hyperplane to separate the class in a better way. Here is one example, one of the mapping function, and you could check it out here. It's actually quite simple. We are calculating based on its original coordinates and using this function, and it will gives out your a new representation like this in a higher dimensional space. Originally, this is in a two-dimensional space, but right now you see here is 1, 2, and 3, and 4, 5, 6-dimensional space. I mean, in the new space, and it's definitely became higher. And there are actually a lot of functions which can be used to map the lower dimensional data to higher dimension. Here, I just listed some example like what's shown here and here. So basically, there is another trick actually used by SVM is SVM is not calculating the mapping one point by point by point. And that is to say, in most of the applications, we got a lot of samples there. If you're going to map each of them into higher dimension, then you conduct the calculation. It takes a lot of time. The other trick used by SVM is if most of the time we are making a decision by calculating the similarity or inner product of two examples, let's see, X and Y. If we're gonna do it in a higher dimensional space, we have to map each of them into that space, then we will calculate the mapped feature vector in a higher dimensional space. Then we have to do it point by point. It takes another time. But it turns out you don't have to do it, because this actually equals to this one. And that means you can actually calculate the inner product in the lower dimensional space, then use the kernel function to map them to the result, the equivalent result in the higher dimensional space. And that trick saves a lot of time. Okay. This is all about SVM. Today we're just taking the SVM as one example. I don't want to frustrate you with too many details. And in next lecture, we're going to learn more about machine learning, about how to find the separating line and how to update different the shape, the model of this decision boundary. So, okay, that's all for today.